Welcome to Operating Systems Lecture 11. So we've been looking at the memory management unit in a typical hardware system, and we've been looking at the x86 MMU in particular. And we said the x86 MMU implements both segmentation and paging, right? So a virtual address is always of the form segment colon offset, CS colon offset, DS colon offset, etc. The segment will point to a segment descriptor. We have seen this in detail, and then the offset is going to be added to the base which is stored in that segment descriptor to get a linear address, right? So far we had been calling this a physical address, but it really is a linear address if paging hardware is also enabled. So further, this linear address goes through another level of translation which we call paging to get you a physical address, okay? Most operating systems, or most systems in general, actually today don't use segmentation hardware for this kind of translation. I mean, in the way that it, in the sense that they typically set base is equal to 0 and limit is equal to, you know, whatever the maximum value is on a 32-bit machine for all the segments. So you get a flat address space irrespective of what segment you're going through, whether you're going through CS, SS, DS, doesn't matter. It's the offset that counts, right? So basically, effectively that means that your linear address becomes your offset, okay? You could imagine an operating system which is actually using only segmentation and not paging. We have discussed this previously, right? In the discussion that I had been having so far, when we didn't discuss paging, we said, you know, it's possible to implement virtual address spaces using segmentation, and in which case, you know, the linear address becomes equal to physical address. And it's possible to do this. You just keep swapping the user's descriptor and keep changing its base and limit depending on which process is getting loaded, right? Right. So it's possible to implement a complete MMU using only segmentation. Well, the only problem is it has some drawbacks, and the drawbacks are, for example, fragmentation becomes a problem, growth of a process is very tricky, and plus, you know, if you are using multiple segments, then the programming model has to worry about which segment I am currently accessing and all that, right? On the other hand, if you have a flat segmented model in which all the segments have exactly equal base and limits, in that case the fragmentation problem becomes more severe, right? Yet another operating system can just use paging hardware, in which case he just sets, you know, all these things to this thing. It still uses the segmentation hardware for things like, you know, for understanding what privilege level I am executing on. Yes, recall that the last 2 bits of the CS register basically indicate whether I am executing in privilege level 3 or privilege level 0, and so that still holds. But apart from that, the offset pretty much has a 1-to-1 mapping to the linear address, right? So base is equal to 0. So in which case he's only using the paging hardware, and yet another operating system could try to use both, right? That's also a possibility. Okay. All right. So now let's look at paging in more detail. So we said, look, paging gets rid of some of the problems of segmentation. So the main problem with segmentation was that it required the entire process to be in one contiguous chunk in the physical memory, right? So entire process memory should be in one contiguous chunk in the physical memory, and so it was creating problems with fragmentation and growth. So as opposed to that, if it was possible to have a mapping between virtual addresses to physical addresses such that the flexibility is more, in which case, you know, a process could be sprinkled across that physical address space, but in the virtual address space it may be contiguous, and you could basically have mappings, arrows going from the virtual address space to the physical address space, right? And we said, you know, it's possible to do that. You know, one has to design it carefully. If so, basically, at what granularity are you going to do this mapping? So we said, let's call the granularity at which you're going to do this mapping a page, right? So for every page, so within a page, contiguous bytes in the virtual address space will be also contiguous in the physical address space. But across pages, that need not be true, okay? Now question is, how big should a page be? We said, you know, page cannot be so small that the data structure to store this translation is so big that it's actually bigger than the actual address space itself. That's, you know, that's ridiculous. On the other hand, it shouldn't be so big that you know, you're wasting a lot of space. So we said, you know, let's say that 4 kilobytes is a reasonable value for a page, and then we said, okay, then if 4 kilobytes is a reasonable value for a page, what's the maximum size a virtual address space can be? It can be 2 to the power 32, right? So 2 to the power 32 divided by 4 KB comes to 2 to the power 20. So you can have at most 2 to the power 20 pages in your virtual address space. Similarly, your physical address space, let's assume, can be at most 32 bits wide. Let's assume that the bus can only take a 32-bit address on the physical bus, which goes to memory. So your physical memory can also be up to 2 to the power 32 bytes, let's assume. Although it may be smaller depending on actually how much RAM you have in your system. In any case, the hardware needs to provision for the maximum possible. So let's say 2 to the power 32 on both sides. So what's the maximum number of pages on both sides? 2 to the power 20. And so you need a mapping from a set of 2 to the power 20 numbers here to another set of 2 to the power 20 numbers here, right? And so this mapping, we said, is if I was to do it in one contiguous table, it will require 2 to the power 20 entries. So I can just have an array which has 2 to the power 20 entries, and each entry basically stores where this page is mapped. This array will actually be pretty big. It will be 4 megabytes if I was to do this. And so assuming that each process has a separate address space, each process will need a separate mapping. And so for each process, I'll need to have a separate data structure of this type. But this sounds very large. 4 megabytes for every process is very large because typically processes are smaller. So let's divide this mapping into a 2-level hierarchy, right? And the first level we're going to call a page directory, which is going to create a mapping from the first 10 bits to a page table. And then the second page, and the page table that you obtain, you're going to use the next 10 bits to get the actual physical address. So you have divided the 2 to the power 20 entries into sets of 2 to the power 10, divided 20 bits into 10 bits, 10-bit lookup. So the advantage of this is, let's say a process is only mapping 64 kilobytes of space, right? So 64 kilobytes of space can be captured in 64 divided by 4, that's 16 pages, right? So 16 pages can probably just, one page table can have up to 1024 entries. So one page table can actually have 1024 pages. So you just need to allocate one page table and fill in those 16 entries here, and just have one entry in the page directory that's pointing to that table at the corresponding offset, right? So let's say my process was having an address space from 0 to 64 KB, right? So what will happen is the 0th entry in the page directory will point to a page table, and the 0th to 16th entries in the page table will point to pages. All the other entries will be invalid, okay? So that way a process which was only 64 kilobytes large needed a page table structure of 8 kilobytes, right? 2 pages. Each of these is a 4 kilobyte structure, so you needed one page directory and one page table. So you needed 8 kilobytes to store the mapping for a 64 kilobyte process, which has a contiguous mapping from 0 to 64 kilobytes, okay? So significant improvement over the 4 megabytes that we had earlier, right? It's a simple thing. You just divide one linear array into a 2-level tree, and you basically only have pointers where there exists a mapping, and for others you just say it's invalid. Okay, so of course the downside of dividing one single table into 2 is what? Number of lookups, right? So number of lookups that you need to do in memory, or number of dereferences that you need to do in memory, has doubled. Earlier you just had to do one dereference to get the physical address. Now you have to do 2 dereferences. First you have to do a dereference here, then you have to do a dereference here before you actually get to the data, right? So here's how it works on x86. There's a special register called the control register 3. We said there are some special control registers in x86. So there's a special register called control register 3, which points to the base of the page directory, okay? And then any linear address that's computed through the segmentation hardware, the first 10 bits are used to index into this page directory to get a page table. The next 10 entries bits are used to index into the page table to get the page, and the last 12 bits are indexed into the page to get the real data, right? The physical address is actually this value plus whatever this offset is, right? That will be the physical address, and that's where the data is going to live in physical memory. Why does the pointer to the page table need to be 20 bits? Great question. Because each page table is also a page. You have basically divided your entire physical address space into pages, right? And you have mandated that page directories and page tables are also constrained to start only at page boundaries, right? A page table cannot be across 2 pages, right. So you basically just statically created a partition of, you basically said every 4 kilobytes you have drawn a line, and you have said that a page table has to live in one of those slots. It cannot actually straddle 2 slots. Okay. So so the number of bits you need to actually understand which slot you have is only 20 bits. Okay. So similarly, the page directory needs to be really only 20 bits. The page table can be addressed using 20 bits, and the page itself can be addressed using 20 bits. Okay. We also said, even although these pointers are 20 bits, it makes sense to actually allocate 32 bits for the entire entry. So this entry is also called the page. This is called the page directory entry. And this is called the page table entry. All right. So let's use the words PDE and PTE for them. All right. So both PTEs and PDEs are 32 bits long. So the last 12 bits can be used for other purposes. And in particular, these last 12 bits are used to store flags. Right. For example, just like in segmentation, you can where you could store whether this segment is allowed to be accessed in unprivileged mode or not. You can say whether this page is allowed to be accessed in unprivileged mode or not. All right. So that's the user flag. Firstly, there is the present flag, whether it says whether the page is actually present. Right. So in this example, where let's say a process has only 64 kilobytes of mapped space, where from 0 to 64 kilobytes and its linear address, then only the first entry will have the present bit set. All the other 1023 entries in the page directory will have the present bit zeroed out. Right. That's what it means that the entry is actually invalid. Similarly, in the page table, the first 16 entries will have the present bit set. All the other entries will have the present bit set to 0. So that's a bit which says whether this page table entry actually means anything or not, whether the hardware should actually dereference it at all or not. All right. Then there is another flag which says user, which basically says whether I should dereference this page table entry only in supervisor mode, or am I allowed to dereference this page table entry either in supervisor or in user mode. Right. So you can do it either in user or privileged mode. And the third thing which it has is whether this page is writable or not. Right. So it gives you another sort of added capability. You can actually, the operating system can actually map certain pages as read only. Right. And we will see why this is a very useful thing to have. So if a page has a writable bit zeroed out, then if a program tries to write to an address that dereferences through that entry, it should generate an exception. Right. And this kind of an exception is called a page fault. So instead of a segmentation fault, now we are talking about paging, so the new name is called a page fault. The meanings are similar. Basically, you are trying to access an invalid address, or you are trying to access a valid address in an invalid way. Right. So a page fault can occur if you are trying to access a non-user page in user mode, or if you are trying to access a non-present page, or if you are trying to write to a non-writable page. Either of these basically mean that the hardware will generate a page fault. And the page fault handler will do the similar thing. For example, it may kill the process, or it may convert the page fault into a signal that it gives to the process. All these just like before, right? Okay.
So these page tables are completely managed by the hardware, or does OS also has a role to play in?
Okay. So yeah, great question. Are these page tables managed by hardware, or does the OS have a role to play in it? The OS sets up these page tables. So the OS sets up the CR3 pointer, for example. Right? The OS sets up the contents of the page directory. The OS sets up the contents of the page tables before it transfers control to the process. But for each memory access, the OS is not coming into the picture. It's the hardware that walks these page tables, or the hardware that reads these page tables. Right? So this process of actually converting a linear address to a physical address is called page table walking, or walking the page table. So the walking of the page table is actually done by the hardware. The operating system sets up the page table. Okay. So the hardware walks the page table, and if there was an error, for example, you're trying to read an entry which is not present, then it will generate a page fault. Right. So yeah. So basically, each of these flags. So when I say there's a flag in the page directory entry, let's say the present flag in the page directory entry is not set. What does that mean? It means there's actually no page in this. There's no mapping here, right? So if the program actually tried to access a linear address that has the first 10 bits map pointing to this entry, which has a present bit not set, then it will generate a page fault right there. It doesn't need to do a second level page lookup at all, right? Similarly, user and writable. So I mean, so it's possible that this entry was present, but it says this entry is not writable. On the other hand, the page table entry, corresponding page entry table says writable. So one of the entries says not writable, the second entry says writable. So the net effect is basically the AND of these two, which means not writable. Okay. Once conversely, this could be writable and this could not be. This could be non-writable, in which case, overall it's non-writable. So the OS can do this at a very fine-grained level at the page granularity. He can do all these writable. You can mark all these writable, and then only pages which are not writable in this particular entry, that those are non-writable. Otherwise, others are writable, and so on. Same thing for user and supervisor, right? So you could have the page directory entry itself could say I'm a user mode entry, which means anybody can access me. But some of these entries are user and some of these entries are supervisor. So once again, you take the AND of these two. So if both of them are supervisor, only or if both of the user bits are set, can the user access that page, right? If for any of these entries, if user bit is not set, then the hardware should generate a page fault if it's executing in unprivileged mode. Okay. All right. So let's see how paging can be used. So we saw how segmentation can be used to implement processes. Question.
Difference between segmentation fault and page fault. Like if we are not using segmentation, then
What is the difference between a segmentation fault and a page fault? Actually, at the Unix abstraction level, a page fault is converted into a segmentation signal, SIG-SEGV, right? So both of them actually map to the same thing. Okay, but at the hardware level, on x86, different exceptions are used to indicate different conditions. So there's a separate exception number for page fault, and there's a separate exception number for segmentation violation.
if we are not using segmentation, it should not occur like.
If we are not using segmentation, a segmentation violation should never occur. Well, that's not true, because you are not using segmentation in the sense that you are not using it to segment memory, but you are still using the privileged bits or the the permission bits in the segment descriptor. So if you try to execute, for example, the user tries to load into the segment selector a privileged descriptor, so that will still cause a segmentation violation. Okay, so it's still possible to have a segmentation violation even in this flat segmentation model, where you're basically mapping the entire space into all the segments. Okay, all right. So let's see how paging can be used. Well, one very simple thing is you set up the page table to basically have an identity mapping, right? So linear address X always maps to physical address X, right? And so that's one way. And how will you do that? You will just say, oh, how big is my physical memory? Let's say it's 0 through M. So you will basically say, okay, 0 through M. Let's say this is my page directory. I'm going to set up the first M by 2 to the power 20 entries here, right? And then each of these is going to point somewhere, and each of them is going to set up all its entries appropriately, right, to exactly the same address. So you could set up a linear, completely identity map between your linear address and your physical address, right? That is probably, that's probably what you will do if you're not implementing multiprocessing and you're not having multiple processes and all that. For example, if you are, using your system, your processor to implement some kind of an embedded system, right? For example, something which does not expect multiple processes to be running, it's just going to run the OS in one way, and you have this paging hardware, you would probably just set up an identity mapping, and or alternatively you could even disable paging, and so it's the same effect, right? So just to get just to understand that you can how you're going to do this, it sort of increases your understanding of how paging works. So identity mapping is easy. The other thing you can do with paging is set it up like segments, right? So you can say okay, so here's my page table. And let me just assume that it's a uniform sort of address space. And so what I'm going to do is I'm going to say okay, let's say this part of the, so let's say this is my physical address space, this is my PA space, all right. So let's say this part of the PA is, or let's say this part of the PA is reserved for the kernel, and this part of the PA is reserved for process P1, this part of the space is reserved for P2, P3, and so on, and let's say this is free, okay, just like what we had in segmentation, and we were implementing it using base and limit. This what I'm going to show you is basically that paging is more general than segmentation, because you can easily do this in paging also, right? Very clear. What you're going to do is basically say that in your page table, so let's say this is physical address 0, and this is something, let's say A, B, C, and D, right? So in your page table, in your page directory, you're going to say, let's say let's say this is VS space. In your VS space, so this was the PS space, and this is the virtual address space. In the virtual address space, each process should see the same set of addresses. So what you're going to do is, in the VS space, if P1 is loaded, then you're going to map P1 to this space, right? You're going to set up the page table such that 0 to B minus A of P1 maps to A to B in physical address space, right? Easy to set that up. You just set up the page directory entries and page table entries appropriately. Then let's say you switch to P2, you will load a new page table, right? And how will you load the new page table? You will change the CR3 register, right? You will change the CR3 register, so a new page table gets loaded, and the new page table will have a similar thing, but it will say 0 to let's say C minus B, and it's going to map this to this, right? So you can just, so in the segmentation model, each time there was a context switch, we were overwriting the segment descriptor with a new base. In this case, each time there's a context switch, I'm overwriting CR3 so that I have a new page table loaded, and I've set up the page table to basically emulate exactly what the segmentation hardware would have done. Yes, we are changing the page directory and also the page tables. So we are changing the entire 2-level hierarchy, right? So assuming that there is no sharing between different page directories, right? Each page directory, so you change the page directory, and consequently you change all the pointers of the page directory also, right? Okay, so when you context switch in the paging world, you're going to replace the CR3, so you're going to have a new page directory, and you can set up your page directory or page table to do this mapping, just like you were doing in segmentation. The only difference is that in this case, the page tables will be different, right? In one case, the page table mappings, the entries which will be present in the page table, or the pointers in the page tables will be different. They'll be pointing to different regions in the physical memory, basically. Question?
Sir, if they are using two separate, for each process separate page directory and page table, the 2-level hierarchy, we have to, in case we update one of them, we have to make sure that those physical addresses are not mapped in other ones.
Yes. So if each process has a page directory and a page and a page table structure, and let's say I update one of them with a new pointer, the OS must ensure that this pointer and wherever this page is pointing in physical memory, that's not it doesn't, that page is not being pointed to by any other page table structure, right? So that's possible for the OS to do, no problem. The OS just keeps track, there's some bookkeeping that these pages are belonging to this process, these pages are belonging to this process, and they are all, you know, disjoint sets of physical pages, and so, and you then create mappings appropriately. Okay. All right. So let's assume that all processes have completely disjoint set of pages in physical memory, and you're going to just set up your page table in such a way that the page table of process P1 is going to point to its pages, and page table of process P2 is going to point to its pages, and each time you context switch, you're going to override the CR3 register. Yes. So for in the GDT, there's a U base and U limit for each process. Yes. Okay.
The segment register will point to that location. They will not going to change.
Yes. Let's say all the segment registers will always point to U base and U limit when the process is executing. Okay.
So that U base and U limit should point to page directly.
That U base and U limit will not point anywhere. Okay. U base and U limit will only be used to compute a linear address. Right. So from the offset, it will compute a linear address, and now the hardware will, what will point to the page directory is CR3. It's a completely, you know, separate register. You're going to use CR3 to actually look into the page directory, use the linear address computed through your segmentation hardware to index into CR3, the first 10 bits, and so on. Okay. All right. So except that there's one thing. So this sounds very similar to how it was done for segmentation, right? The only difference really is in this case I'm changing the page tables themselves. In that case I was just changing the segment descriptor, right? The difference here is that the kernel is also, you know, I said that in this model, let's assume that the segmentation is completely flat. So even the kernel's segment descriptor also has base is equal to 0 and limit is equal to 2 to the power 32 minus 1, right? So the kernel is also, you know, the kernel is also not using the segmentation hardware at all, let's say, right? In which case, you know, somebody else, so the virtual address to physical address translation is just going to take the offset and make that the linear address, and now the linear address has to be converted to physical address by your paging hardware. Right? So the kernel's linear address is likely, it's possible that the kernel's linear address needs to be converted to physical address by the paging hardware, right? And so what you do is you inside the page table of every, or inside the VS space of every P1, you also map the kernel somewhere, right? So the kernel shares VS space with the process. Okay, let's see, you know, this. So basically, let's take some concrete examples. How does it work in Linux? All right, so how does it work in Linux? Every process has an address space which can go from, you know, by definition on a 32-bit machine, you can at most have 0 to 2 to the power 32 minus 1, except that you say that a process is not allowed to access the entire 0 to 2 to the power 32 minus 1. If you are compiling a process for Linux, or if a process should be able to run inside Linux legally, then it should never access an address beyond, so, you know, this, let me call it 4 GB just to make it more readable. So 2 to the power 32 minus 1 is, let's say, 4 GB, and so you shouldn't ever access an address above 3 GB, right? So a process is constrained to access addresses only within 0 and 3 GB. The addresses from 3 GB to 4 GB, the virtual addresses, are reserved for the kernel. So that's where the kernel is mapped. Okay, so let's say this is P1. So typically what will happen is P1 is mapped 0 to, let's say, some address, you know, 100 KB, and all this is not used. Okay. And then there is P2, which also has 0 to, you know, let's say 200 KB this time, and but also has the kernel mapped from 3 GB to 4 GB. Right. So the kernel also ensures, basically, while setting up the page table, that its own pages are always mapped in a certain address range. of the VS space. So if, for example, there's a transition from user to the kernel and the kernel wants to access its own data structures, it can just use one of these addresses from 3 GB to 4 GB to start and accessing its own code and data, for example. Because in this scenario, we are not using segmentation at all. What was happening in segmentation? Each time there was a switch from user to kernel, CS was overwritten. And CS had a different base, right? And so that way the kernel, you were now actually accessing kernel's memory and not user's memory immediately. And the first thing the kernel will do is load other segment registers so that, apart from the code, other segments are also pointing to the kernel. But in this model, when everything is flat, and the kernel is also using a flat model, the user is also using a flat model. When you switch CS, you're still in the same linear address space, right? And but you need to say that now I want to access kernel's data, or now I want to access kernel's code. So the way it's done is CS, the offset of CS is still 0, but the EIP, there are certain EIPs that are reserved for the kernel. So in particular, the EIPs above 3 GB are reserved for the kernel on Linux. Right? So in the interrupt descriptor table, for example, the CS colon EIP, the CS base of CS, if I'm not using segmentation, the base of CS will be 0, but the EIP will be some address above 3 GB, typically. That's where the handler will live. Right? And so because the offset is above 3 GB, the linear address will also be above 3 GB, and now it will go through the paging hardware, and you will basically reach the kernel's space. It's the job of the kernel to ensure that the paging hardware translates the address 3 GB and above to the right place in the physical memory, and that it can do by setting up the page table in such a way. So each process's page table not only maps that process's address space, but also maps the kernel's address space at the top in Linux, right? On Windows, this is typically the model followed in many operating systems. Similarly, in Windows seems to sometimes need more space, so it can actually take 2 GB. It actually takes the top 2 GB for its own kernel on the 32-bit machine, but it actually allows you to actually change it if you want. Right? So depending on and this is part of the specification of the operating system. So if you're compiling something for Linux, then you should ensure that your application will never access an address above 3 GB. Okay, so it's part of the interface. The compiler should be aware of that, or if the programmer is assembly programmer, he should be aware of that. And how do you do protection? How do you ensure that the user is never able to access kernel's data or execute kernel's code? The flag, right? The user flag. So the user flag is off for these mappings of kernel. So for all the kernel mappings, the user flag in the page directory entry and the page table entry is 0. For all the other entries, the user flag is 1. So the user can never access the kernel. But if there's a trap, then CS gets reloaded, and the last 2 bits of CS will become 0, and now it can access the upper regions of memory, virtual address space. Question?
So these pages are common across processes like
right. So just like we saw that in segmentation, the kernel remains constant, right? The kernel doesn't move. The kernel in the physical address space remains sort of there, and the mapping for the kernel remains constant. Similarly, the mapping this remains constant. So the same entries which get copied in every page table, or every page directory and page table of every process.
Kind of an exception for overrule that every page should point to a different physical entity. So here's an example where we are breaking the rule that every page table should be pointing to a distinct set of pages, right? Here's an example where 2 different processes, page tables, can be pointing to the same page in physical memory. Yeah, great point. And actually there are more examples which we will discuss later. Question? Yes, sir. This kernel address space, does this also have the kernel stack for that process?
Does this also have the kernel stack for the process? The kernel address space? Yes.
So, won't the kernel stacks for 2 different processes different from each other?
Right. So let's look at how the kernel stack gets switched. So we said that if there was a trap while I'm executing in the user mode, both the CS will get overwritten and SS will get overwritten, EIP will get overwritten and ESP will get overwritten. And so what does the OS need to ensure? That the EIP is an address above 3 GB and the ESP is also an address above 3 GB. Okay? And within this kernel space, you could be having multiple stacks, one per process. So actually, in the kernel space, you're actually having all the stacks of all the processes, all the kernel stacks, assuming the process model of the kernel. So in the kernel space, you will have all the stacks of all the processes, but it's all inaccessible to the user. The user cannot access it, right? So it's just that the kernel has mapped its entire data structure and code into the user address space. So if there's a trap and a flat segmentation model, then you straight away go to the kernel address space in both for EIP, the program counter, and the ESP, the stack pointer. Okay, and then you also change your other sort of segments and all that. Okay, question is, why do I need the entire kernel to be mapped inside the process address space? Couldn't I have just mapped the kernel stack in the process address space? Just one, let's say whatever size I want to have for the stack, kernel stack, that's what I'm going to put it in the. But what about the code? So the program counter, you'll also need to put that. So the handler needs to be there, right? And so the handler is going to make more calls. So you could potentially say that, look, I don't, this 1 GB of space taken away from the process seems too costly. And so what I want to do is actually have a very small sort of handler inside, which is not 1 GB, but let's say few hundred KBs, and that handler is actually immediately going to switch the page table, and then he's going to execute the kernel logic. That's a possibility, right? There are pros and cons to doing that. This actually works. This is one of the best performance kind of designs. So there have been multiple designs of operating systems that have been proposed, but this is sort of the most popular design. And one reason this is the most popular design is it's the most performant design. Okay, or I should qualify this statement. This is a controversial statement. It may not be the most performant design, but it's the easiest to get performance out of this design. Right? And this is a design that your mainstream kernels use. Linux, Windows, XV6 is what we're going to be studying starting next time. PinTOS, which is going to be your programming assignments. All right. So so basically, this is how. So the kernel basically maps itself in every process address space, and if there's a trap, it can immediately transition without having to do anything, and the kernel can now execute happily inside the process address space. Basically, there's one difference, that the kernel needs to be aware that it should only be accessing, it should be living in a certain address range. In segmentation case, the kernel could have mapped itself from 0 to something, right? Because CS base has been changed, so you're pointing somewhere else. But in this case, the offset needs to be within a certain range, 3 to 4 GB, let's say, on Linux. Okay. So let's see what happens on the timeline, just like we had seen for let's say this is boot time, just like we had seen for the process. So what happens is, at boot time it will first set up its segmentation table, and now in this case it will just set up the segmentation tables to completely identity mappings, 0 and 2 to the power 32 minus 1. Then it will set up its own page table, which will be, let's say, an identity mapping, and it will enable paging in the hardware, right? And so it's the kernel's page table that's getting loaded here. Then the kernel will load itself in a certain address space. So the kernel has been compiled to assume that it will be living in a certain address range, right? So the kernel's EIP and all these the program counters will always be in that address range. And so when it loads the kernel, and the core kernel starts executing, so let's say, so initially you start executing in physical address space. So kernel is living from 0 to whatever maximum value you have. Then what the kernel does is it loads itself from, while it's executing, it loads itself in the top address space also. So it first sets up page table. So enable paging. It sets up the address space, and now it says, let's map myself in the new page table at the top. So it's going to map itself on the top also. So it's going to say 3 GB to, let's say, 3G plus M. Right? So it's going So this is where it gets loaded, and now it starts running from here, and now it's context switches to the first process. It starts the first process, and so the kernel lives here. I want to say K, and the process, let's say, lives here, P1, right? And then it again context switches. When it context switches, it actually, it executes. So when it context switches, a trap occurs while it was executing here. When the trap occurs, it starts executing here. Here it does the appropriate changes in CR3 in the page table. So when it does the page table change, it actually reaches here. It's changed the address space. It's changed CR3, and now it calls return to get to resume execution of process P2, right? So process P1 is executing in user mode. A trap occurs. You switch to kernel's address space in the same page table. The kernel in that page table, while it's executing that page table, creates a new page table for process P2 if needed, maps itself in that new page table, switches the page table. Because it had mapped itself at exactly the same addresses, when it switches itself, it's not like the carpet has been dragged out under its feet, because the same addresses are still valid, right? So the new page table has the kernel mapped in exactly the same place where it was mapped in the old page table. So when you switch, it doesn't matter, right? The kernels can still execute. It's just the user space address space that has changed, and now you can return back using the irate instruction to the process, and now the process P2 can start executing.
So, but kernel, there was already a kernel space in the P1 page table. So why did it need to do a context switch?
So let's say the kernel has decided that it wants a context switch from P1 to P2, right? So it needs to load the new P2's page table, but the nice thing is that P2's page table also has the kernel mapped at exactly the same position. So when it overwrites CR3, its addresses are still valid. So the next instruction pointer will exactly go to the same physical location still, right? And now the next thing it will do is basically go to user mode, and this time it will see P2 there.
So all the kernel spaces in each of the processes are exact replicas of each other.
All the kernel spaces in each of the processes are they replicas? Well, they're actually pointing to the same place. So they're not replicas, they're shared. They're not copies, they are just shared with each other.
But page tables are replicas.
Page tables are replicas. So the kernel space itself is not replicas, the page tables are replicas for those particular entries. Not all the entries, just those particular entries which are mapping the kernel. Okay? Okay. All right. So let's see some nice things that you can do with paging. You can do something called so firstly, paging solves the problem of fragmentation and growth in a large way, right? Because now if a process needs to grow, all it needs to do is, let's say this is the VA space, and this is the PA space. So let's say the process is mapped in 0 to capital M, but these are pages which are mapped here. Let's say it has two pages. One is mapped here and the other is mapped here. So let's say this is P1, so these are P1's pages and these are P1 pages. And now there are other pages like P2's pages, P3's pages. So there are two, let's say two P2 pages, one P3 page, and now there's all this empty space. Now if I want to grow M, all I need to do is, create another mapping for another page, allocate another page here, P1, and create this mapping here. Right? So growth is very easy. No problems of fragmentation. You just sort of allocate a new page in the physical address space, and you create a mapping in the page table so that the virtual address space grows. Okay, so growth is no problem. Fragmentation is no problem because the mappings don't need to be contiguous. If there was enough space if there are enough pages for the new process to fit in, it will get fit in. It's not like they need to be contiguous. All right. Okay, so it solves fragmentation. The other nice thing it can do is what's called demand paging. Right. What is demand paging? let's say I created a new process, right? And let's say this process is ls, right? So let's say this is ls, and ls maps its code in, let's say, 0 to capital M, hypothetically. And let's say there's this disk, right, which has this program file called ls executable, right? ls executable. Now when you actually say ls, one way to implement the exec system call in the OS is to actually copy the entire contents of the ls executable into physical memory and create this mapping, right? That's, upfront you allocate that much memory, you copy the entire disk contents to memory, create the mapping, and start the process running. And optimization over that is that you actually don't read the disk into memory upfront. You just create an address space from 0 to M by reading the executable, and then you basically just store some meta information in this address space saying that, look, right now these pages are not present, but if the user tries to access this page, then here's where you should get it from on disk. So here's the disk log from where you should get this particular page from, right? So for example, if ls was a large program, let's say the program was, let's say, 1 megabytes large, but typically when you type ls, you're only going to be executing, let's say, 100 kilobytes of code somewhere, and almost let's say 4 kilobytes of data. So you only needed those 104 kilobytes in memory. You didn't need to read the entire 1 megabyte into memory. So what you do is, demand paging helps, but the OS doesn't know, what may get executed in future. So, but demand paging helps. It creates the address space for the entire 1 megabyte. It maps the first page of the page containing the instruction, which is the first instruction, into memory, and transfers control to that instruction. If that instruction happens to execute some other address which is not currently mapped, what will happen? Page fault. The operating system will come into action. It will figure out, actually the process is not doing anything illegal. It's I who is playing tricks under the rug, right? And so I should actually stick to my contract. And so that's when he'll basically pick up the page, paste it into physical memory, create the mapping, and restart the instruction, right? So this is demand paging, very useful optimization. In fact, we discussed this. We discussed fork and exec, right, in Unix, and we said, and then we said, oh, Windows has this create process, right? And we said, look, fork seems very wasteful because you're going to actually copy the entire process in from disk to memory and all that. But the reason Unix designers at that time thought that it's not a big problem, you can actually fork is not so inefficient, is because of demand paging. At that time, memories were really small, so most of your program code and data used to live on disk, right? And so fork was basically just forking a process just involved creating a new page table and updating and having the same pointers, shared pointers, to the disk. And so fork was really cheap in that sense. And if the next thing the process is going to do is exec, no problem. You actually didn't waste much work, right? So at that time it seemed very natural, and so fork and exec was a nice interface, because given that demand paging was a very, very possible optimization. So I mean, optimizations also dictate your programming models, right? Nice example of this. Another thing you can do is copy on write, right? So what's copy on write? Let's say here's a process P1, and it forks another process P2, right? And let's say it's not the old world. In the new world, the processes memories are large, so the process is actually living in memory, right? So once again, fork is actually one way to implement fork is that you create a page table for the new process, and you basically point the page table entries of both P1 and P2 to the same physical pages, except that you mark all those pages read only, right? Because if one process writes, you don't want that to be visible to the other process, so you mark all those pages read only. So the entire space is shared except that it's now become read only. Now if one of those processes tries to write one of those pages, then immediately there will be a page fault, and you will just copy it at that time. So that's called copy on write, right? So you actually shared the pages, and assuming that the child process was going to call exec immediately, it's actually not going to write to any page, right? And the page table is going to get overwritten. So fork is again very cheap, even in the memory world. All right. Okay, good. So let's stop here.